Got no time? Got a test? It's time to cram.
Queen Ratnamanjuri had a will written that described her fortune of Ratnas and also included a puzzle. Her son Khoisnam and their 99 relatives were invited to the reading of her will. She wanted to leave all of her Ratnas to her son, but she knew that if she did so, all their relatives would pester Khoisnam forever. She hoped that she had taught him everything he needed to know about solving puzzles. She left the following note in her will. I have created a puzzle. If all 100 of you answer it at the same time, you will share the Ratnas equally. However, if you are the first one to solve the problem, you will get to keep the entire inheritance to yourself. Good luck. The minister took Khoisnam and his 99 relatives to a secret room in the mansion containing 100 lockers. The minister explained each person is assigned a number from 1 to 100. Both the lockers and the participants are numbered 1 through 100. Every locker begins in the closed position. Person 1 takes the first turn toggling every multiple of 1, opening every single locker. Person 2 then toggles every second locker, closing the already open even numbers. Person 3 toggles every third locker, closing locker 3, opening 6 and closing 9. This continues 100 people have finished. To win the race against his relatives, Khoisnam needs to identify the final state of the lockers without physically simulating every turn. Instead of tracking every person, we can find the answer by focusing on a single locker. Let's look at locker number 10. Locker 10 is touched only by the people whose numbers divide evenly into 10. Person 1, 2, 5 and 10. These are the factors of the number. These factors appear in a pairs 1 multiplied by 10 and 2 multiplied by 5. 4 factors result in 4 toggles. Person 1 opens it, 2 closes it, 5 opens it and 10 closes it. Any locker with an even number of factors will always end up closed. Apply that factor logic to locker 36. Will it be open or closed? The factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18 and 36. Unlike locker 10, this locker has 9 factors, an odd number. The factors still pair up 1 and 36, 2 and 18, 3 and 12, 4 and 9. But the number 6 is left alone because 6 multiplied by 6 is 36. It does not have a distinct partner to toggle the door a second time. An odd number of factors means an odd number of toggles, which leaves locker 36 in the open position. This property is unique to perfect squares because they are the only numbers with an odd number of factors. They are the only lockers that remain open at the end of the game. Khoisnam realizes he only needs to list the perfect squares between 1 and 100 to find the open lockers. The open lockers are 1, 4, 9, 16, 25, 36, 49, 64, 81 and 100. To reach the gems inside the inner safe, Khoisnam must provide a second passcode. The numbers of the first 5 lockers touched exactly twice. A locker touched twice is a number with only 2 factors, 1 and itself. These are prime numbers. The final passcode is 2, 3, 5, 7 and 11. The mechanics of the game are defined by these three properties. Number 1. Lockers with an even count of factors and up closed. Number 2. Perfect squares have an odd count and stay open. Number 3. Prime numbers are touched exactly twice. By identifying the factors of each number, Khoisnam determines the state of every door without performing hundreds of manual toggles. He uses number theory to find a solution instantly. Let us begin today's class. Does every number have an even number of factors? What are factors? Factors divide evenly. A factor is any number that divides into another number without a remainder. Let us take one example, number 12. The factors of 12 are 1, 2, 3, 4, 6 and 12. That is 6 factors total. They always come in a pairs. Look, 1 multiplied by 12, 2 multiplied by 6, 3 multiplied by 4. Every factor has a partner. So, most numbers have factors that come in perfectly matched pairs, giving an even total count. We have already seen 12. There are factor pairs. There are total 6 factors and number of factors are even. Let us take example of 20. So we can get the pair of factors as 120, 210 and 45. Again here 6 factors and total number of factors are even. Is this pattern applicable to perfect squares? So first of all, let us learn and understand what are perfect squares. Numbers like 1, 4, 9, 16, 25 and up to infinity made by multiplying number by itself. If we check their factors, then their factors are 1, 3 and 9 for number 9. So there are only 3 factors and odd number. If we take the example for 16, then the factors of 16 are 1, 2, 4, 8 and 16. Again here 5 factors and they are also odd. Why perfect squares are different? Let us check this graph. Distinct versus identical. So for mixed example, there are 2 entries and we are getting regular pairs where distinct factors counted twice. In a square number, single entry, perfect square matching factors counted only once. So when a number pairs with itself, it only gets counted once, breaking the even pattern. So for the regular pairs, the two numbers are always different. And for perfect square pairs, one pair has a matching numbers like 3 multiplied by 3. The middle factor counts only once. So the result what? Okay, one fewer factor than expected. The total becomes odd. So you can check here how and why perfect square are different. Let us take more perfect square example. For then factors are 1, 2, 4 and the 3 factors and odd. 16 factors are 1, 2, 4, 8, 16. 5 factors and again odd. Let us take 25, then factors are 1, 5, 25. There are 3 factors and odd. Every perfect square follows the same rule. One self-paired factor always makes the count odd. So let us check the pattern. For regular numbers, factors pair up perfectly even number of factors. For perfect squares, one pair matches itself odd number of factors. So the answer is what? No, not every number has an even number of factors. In the beginning, we had question, Does every number have even number of factors? Then the answer is what? No. The reason is given here. Perfect squares are the only numbers with an odd number of factors. If factors are even, number is not a perfect square. Pairs match up and the count is even. All other numbers have an even number of factors because their factors pair up perfectly except when a number is multiplied by itself. Perfect square only is a middle factor, stand alone, and it gives odd count. Patterns in perfect squares. Discover the hidden rules behind square numbers and learn to predict them without a calculator. There is a challenge. Complete the table. Find the squares of the first 30 natural numbers and fill in the table given below. Let us check some number. 1 square equal to 1, 2 square equal to 4, 3 square equal to 9, 4 square equal to 16, 5 square equal to 25. This you have to complete. Same way, 11 square equal to 121, 21 square equal to 441, and you will complete up to 30 square. Your mission: find the squares of the first 30 natural numbers. Record your results in the table. Look closely. Hidden patterns are waiting to be found. Don't rush to the answer. The journey of noticing is the learning. What did you find? Let us check. Last digit pattern. Is this such a interesting mystery? Look at the last digit of the first 10 perfect squares. 1 square equal to 1. This is the one digit only, means last digit is 1. 2 square equal to 4. Last digit is 4. 3 square equal to 9. Last digit is 9. 4 square equal to 16. Last digit is 6. 5 square equal to 25. Last digit is 5. 6 square equal to 36. Last digit is 6. 7 square equal to 49. Last digit is 9. 8 square equal to 64. Last digit is 4. 9 square equal to 81. Last digit is 1. 10 square equal to 100. Last digit is 0. Do you notice something? Only certain digits appear. What are they? Did you notice properly? These are the digits as a last digit of the perfect square. And these are the impossible last digits: 2, 3, 7, and 8. So let us understand the rule. Rule number 1. Perfect square only end in 0, 1, 4, 5, 6 or 9. Second rule, numbers ending in 2, 3, 7 or 8 can never be perfect squares. This pattern repeats forever, no exceptions. Quick test. Is 347 a perfect square? Think. Pause the video and then check your answer. Zeros at the end, a doubling pattern. In this video, we will learn so many patterns for a square number and a cube number. If you make a square of 10, then you will get 100. If you make a square of 100, then you will get 10,000. If you make a square of 1000, then you will get 1,000,000. Every time you square a power of 10, the number of trailing zeros doubles. This is because multiplying tens adds their zeros together, as 10 multiplied by 10 equal to 100. So this is known as a zeros at the end, a doubling pattern. The zero rule. The formula: if a number ends in a n zeros, its square ends in a 2n zeros. How it is easy to learn and understand? Second rule, always even. Perfect square always have an even number of trailing zeros as 0, 2, 4, 6. What is impossible here? You can never have 1, 3, 5 or 7 zeros at the end of a perfect square. Odd versus even. Parity preserved. Odd numbers stay odd. You can see here, look. Even numbers stay even. 4 square equal to 16, 6 square equal to 36, 8 square equal to 64. So, odd multiply by odd equal always odd, and even multiply by even always even. A number's odd or even nature, its parity, is always preserved when squared. No surprises? Why these patterns work? You can see here very clear three reasons for that. Let us see first reason, multiplication rules for the last digits. Only the last digit of a number determines the last digit of its square. As a 2 multiplied by 2 equal to 4, 3 multiplied by 3 equal to 9. The pattern locks in and repeats every 10 numbers. Second, addition of exponents. When you multiply numbers like 10 to the power n multiply by 10 to the power n, the exponents add. That you know, the law of exponent. You get 10 to the power 2n. Zeros always double. That is why you can never have an odd number of them. Third reason, parity. Odd multiply by odd and even multiply by even. Odd numbers times odd numbers are always odd. Even numbers times even numbers are always even. Squaring never changes a number's parity. Note down properly. By end of this topic, what is your challenge? Complete the table. Predict 47 square without calculating. And how many zeros in a 10,000 square? Now let us learn perfect squares and their square roots. Discover the patterns hidden in numbers. Question number 1. Which numbers have 6 in the units place? A perfect square can end in 6, but only when its square root ends in a 4 or 6. Let's check each number. Look, here we are going to learn square root. A perfect square can end in 6, but its square root ends in a 4 or 6. Note down properly. Let us take example. Look, 4 square and 6 square. 4 square equal to 16. 6 square equal to 36. You can see here in a both number last digit is 6. These are the perfect number made by the two different digit 4 and 6. Now if you take the square root of 16 again, then what you will get? 4. And if you take a square root of 36, then what you will get? 6. So here we can see that if the last digit is 6 of a perfect square number, then its square root may be ends in digit 4 or 6. Okay. So let us take this number. If you square 382, then the number ends with a 4. Number does not end with a 6. Okay. Same way, 342 square ends with 4 and does not ends with 6. But if you take number 46 square, then it end with 6. So our answer is yes. Because why? If you take the square root of this number, then square root may be ends with 6 here. Same way, another number is 564 square. If you make the square, then number ends with 6. So it is a yes. And if you take the square root of this number, then you may get 4 as a last digit. Example 5, 742 square, it ends with 4 and does not end with 6. Same way, 82 square, it ends in a 4 and does not ends in a 6. What are perfect squares? A perfect square is a number you get by multiplying a whole number by itself. We write it using the exponent 2. Look again. 1 square equal to 1, 1 multiplied by 1 equal to 1. 2 square equal to 4, 2 multiplied by 2 equal to 4. With the picture slide also you can learn here 1 square equal to 1 means 1 slide here. Here 2 square equal to 4 means 4 slide here. 3 square equal to 9, 3 multiplied by 3 then here 9 slide. 4 square equal to 16, 4 multiplied by 4 equal to 16, here 16 slide. Same way, 5 square equal to 25, then 5 multiplied by 5 equal to 25, 25 slides are there. Look at this picture and motivate yourself. I am not going to read this thing. Pause your video and read everything from this picture. Read every slogan as well as what are written in this staircase. I hope you must be motivated. So let us continue our journey. The successive subtraction method. There is a clever way to check if any number is a perfect square. Is calculator needed for that? No. In this method, keep subtracting consecutive odd numbers. Take odd numbers one by one. This is our first step. In step number 2, watch for 0. Are you getting 0 or not? Wait for that. If you land exactly on 0, the number is a perfect square. And last step, step 3, count the steps. The number of subtractions you made equals the square root. Means how many steps you have carried out. These are the square root of your number. Let us take one example to understand this method. Is 25 a perfect square? Let us check. So, first we subtract 1. What we are getting? 24. This 24 we carry here. Now, second consecutive number is 3. What is the result then? 21. This 21 we carry here. What is the next consecutive odd number? 5. Then result is 16. This 16 we carry here. Next consecutive odd number is 7. Result is 9. Then last step, the next consecutive odd number is 9. 9 minus 9 and the result is 0. Each step subtracts the next odd number in the sequence 1, 3, 5, 7, 9. What does this tell us? We reached exactly 0 after 5 subtractions. Therefore, 25 is a perfect square number because we got 0. And the square root of 25 equal to 5 because 5 subtractions are there. What is the conclusion? The count of subtraction always equals the square root. Try it with 36. Next question. Find 36 square using the pattern. Oh, we are going to learn new pattern. Instead of multiplying 36 to 36 from scratch, we can use a powerful algebraic shortcut. What is the shortcut? Let us see. You know this algebraic identity. N plus 1 bracket over square equal to n square plus 2n plus 1. Now, here n is what here? 35. Because why n is 35? Look, n equal to 35. And your n plus 1 is 36. So n equal to 35 and hint is given for 35 square as 1225. So look, in this formula n square value is given already. Look. So 2n is what? Okay, you have to multiply 2 to 35. Look, this is the pattern. 2n plus 1 means in your given number you have to add 2n plus 1 where n is your given number 35. So 2 into 35 is 70 plus 1. So if you add 71 to your given number 1225, then you will get the result. So is this interesting pattern? Now next question, finding odd numbers. There is a simple formula that gives you any odd number in the sequence instantly. Let us take example of 36th odd number. This is our question. Okay, find the 36th odd number in the sequence. Then what you have to do? You have to use this formula. Look, the formula is there 2n minus 1. To multiply by given number 36 minus 1. Result is 71. Means your 36th odd number is what? Okay, 71. So this formula for nth odd number is very useful to find any odd number in the sequence. So again, note down properly, nth odd number is always 2n minus 1. Also you can verify by taking n equal to 1, n equal to 2 and n equal to 3. Look, if you take n equal to 1, then your first odd number is 1. If you take n equal to 2, then your next odd number is 3. If you take n equal to 3, then your third odd number is 5. And the same way, if you take n equal to 36, then your odd number is 71 in the sequence. Next question, numbers between consecutive perfect squares. The pattern in action. The manual method is given here to calculate numbers in between given square number. After going through this method, what is your conclusion? Tell me. Look, in between 1 square and 2 square, there are two numbers. So count is 2. In between 2 square and 3 square, there are 4 numbers. And count is 4. In between 3 square and 4 square, there are 6 numbers. So you can see here, if the number increases in that way, then it is becoming tedious method for you. If I write the example as a numbers between 140 square and 141 square, then what? Then it will take a lot of time of your, and after consuming this time, it is possible you may get a wrong answer. Let us see the rule for that. Okay, between n square means what? Okay, 140 square, look. And look, you add 1, then it is a n plus 1 square, 141 square. There are always exactly 2n number. 2n means n is what? Smaller number. So 2n number. So what you have to do here, 2 multiply by 140. Look, in a fingertip answer is there, 280. So in between 140 and 141 square, there are exactly 280 numbers. Same way, in between 10 square and 11 square, there are 2 multiplied by 10 equal to 20 numbers. Is this interesting or not? So, after learning this concept, will you be cheered like these students or not? Key takeaways. Number 1. Patterns are predictable. Perfect square follow rules you can rely on every time. Number 2. Odd numbers are the building blocks. Every perfect square is built from consecutive odd numbers added together. Number 3. Shortcuts save time. We have seen in the previous slide how quickly we found the count of numbers between two given perfect square numbers. So formulas like n plus 1 bracket over square equal to n square plus 2n plus 1 let you find answers without heavy calculation. Number 4. Math is everywhere. Look for the patterns. Once you see the pattern, the whole number system opens up. Next topic, perfect squares and triangular numbers. An interactive exploration of patterns in mathematics for grades 8. Let us see. What are triangular numbers? Look the picture. Pause your video and try to complete this empty box. Do you remember triangular numbers? Look how 1, 3, 6, 10 and 15 construct a right angle triangle here. Can you see any relation between triangular numbers and square numbers? Extend the pattern shown and draw the next term. If you add them, look 1 and 3, then what you will get? 4, and 4 is a square of 2. Same way, if you add 3 with 6, then what you will get? 9, and 9 is a square of 3. Same way, if you add 6 and 10, then what you will get? 16, and 16 is a square of 4. So same way, here you have to add 10 plus 15 and write your result. Triangular numbers are numbers that can be arranged into a neat triangular dot pattern. The sequence goes 1, 3, 6, 10, 15, 21 and so on. Growing rows. Each new row adds exactly one more dot than the row above it. Look this pattern. Visual structure. The triangular shape reveals the mathematical pattern hidden inside the numbers. Formula. The nth triangular number. This is the formula. Also we can write in this way, n into bracket n plus 1 divide by 2. Discovering the connection. Can you spot the relationship between triangular numbers and perfect squares? Here is a hint. Look at what happens when you add two consecutive triangular numbers together. That already we have seen in the previous slide. Look, two consecutive triangular numbers always add up to a perfect square. Every time. Let us very quickly recapitulate what are perfect squares. I just wait here. You revise your concept here. Next topic, square roots. Practical problem. The area of a square is 49 square centimeter. What is the length of each side? We know that if we multiply 7 with 7, then we are getting 49. And 49 is a square of 7. So when we take the square root of 49, then we will get the 7 as a square root. So this thing we are going to learn here. Okay, the square root is the reverse operation. Look, the reverse operation of squaring. It answers what number times itself gives this result. So 7 square is 49. Then if we take the square root of 49, then it is a 7. So what is our answer? A square has area 49 centimeter square. So its side length is a 7 centimeter. Now let us learn consecutive odd numbers pattern. Every perfect square is the sum of consecutive odd numbers starting from 1. This reveals the beautiful layered structure inside every square. Recall that every square can be expressed as a sum of consecutive odd numbers starting from 1. So look, 1 is a 1 square. Now 1 plus 3 equal to 4, and it is a square of 2. So here the addition of two first consecutive odd numbers. Now first 3 consecutive odd numbers will give 9, and it is 3 square. Same way, first 4 consecutive odd numbers will give 16, and it is a square of 4. So how we are understanding if we are adding 4 consecutive odd numbers, then we have to simply make the square of 4. Did you learn? Now next topic, prime factorization test. Find whether 1156 and 2800 are perfect square using prime factorization. So use prime factorization to identify perfect squares. The rule is simple. Every prime factor must appear an even number of times. That we have learnt ahead. So if you make the prime factorization of 1156, then you will get 2 and 17 as a prime number of their respective exponent. Both factors appear twice. Yes, this is the perfect square number. Now look, 2800. If you make the prime factors of this number, then you will get 2 to the power 4, 5 to the power 2, and 7 to the power 1. So 7 appears only once here. So that is why this number is not a perfect square. There is a one problem solving challenge, the game. Consider the following situations. Aribam and Bijo play a game. One says a number and the other replies with its square root. Aribam starts. He says 25 and Bijo quickly responds with 5. Then Bijo says 81 and Aribam answers 9. The game goes on till Aribam says 250. Bijo is not able to answer because 250 is not a perfect square. Aribam asks Bijo if he can at least provide a number that is close to the square root of 250. Pause the video and try and understand the problem. Aribam says a number, Bijo must respond with its square root, but only if it is a perfect square. First Aribam says 25 and Bijo answer 5, so it is correct. But then Aribam says 250 and Bijo not reply. Why? Because 250 is not a perfect square number. So pause your video and try to find the answer and predict your answer from this. What should Bijo reply? Next real world application, Akhil's cloth. Akhil has a square piece of cloth of area 125 centimeters square. He wants to know if he can cut out a square handkerchief of side 15 centimeter. If not, he wants to know the maximum size handkerchief that can be cut out from this piece of cloth with an integer side length. Pause the video and read the question properly. Akhil has a square cloth with area 125 centimeters square. He wants to cut a 15 centimeter side. If you multiply 15 multiply by 15, then what? Can he do it? So definitely, if you try for 125, then approximately you can get 11.2, and it is not a perfect square. So the cloth is only about 11 centimeter wide. Akhil exactly needs length 15, and as per him, the area should be 225, but his cloth is too small. So what is Akhil's challenge? What is the largest perfect square handkerchief Akhil can cut from his 125 centimeter square cloth? An answer already we found here. Let us solve exercise with a step-by-step explanation. Question number 1. Which numbers are not perfect square? We know that 2 is there. So here there is no need to take square root in that way, because we know that k2 never be in the perfect square number. Same way 8, same way 7, but 9 may be. And if you take the square root of 1089, then exactly you will get 33. And that is why it is a square of 33. So answers 1, 2 and 3 are not a perfect square, and number 4 is a perfect square. Question number 2. Which has a last digit 4? Identify which number ends in the digit 4. So you can see clearly 64 has a last digit 4. Question number 3. Find the value of 126 square. Earlier we had learned the pattern. Look, recall this pattern. A square and 2a plus 1. 125 square is given already. To find square of 126. Okay. So what we have to do? This is the value of 125 square. Here 2n plus 1. So keep all the value, then you will get easily by the pattern 15,876. Again I am writing the pattern 2n plus 1. Okay, where n is the given number 125. Question number 4. Side length of a square with area 441 meters square. We need to find side of this square. 441 is a perfect square number and it is given as a area. We know area formula. So after taking the square root of 441 by prime factorization method, we can get 21 as a answer. So our answer is the side length is 21 meters. Also do notice this diagram. You can verify your answer by this way. Next question. Find the smallest square number which can be divisible by 4, 9 and 10. So there are the steps. Look, Look picture, very interesting and we can learn easily. First step, find LCM. So find the LCM of 4, 9 and 10 by this method. 4, 9 and 10. Then you will get the LCM 180. So 180 if you write in the exponent form, then you will get 2 2 time, 3 2 time, but 5 is only once. So factor 5 has an odd power. It is not a perfect square yet. So if you multiply this number 180 by 5, then you will get 900. And then 900 can be, 900 is also perfect square number. Look, it is a perfect square number and its square root is 30 and it is divisible by, 900 is divisible by all given number 4, 9 and 10, and it is a very smallest number. You could not get any other number than 900 which can be divisible by 4, 9 and 10. Next question, multiply 9408 to make it a perfect square. So first step, you have to make a prime factorization of 9408. You can see here 3 having even power, 7 having even power, but 2 having odd power. Means 1, 2 is unpaired. 2 appears 5 times, means odd. Needs one more factor of 2. So multiply by 2 to get it as a perfect square number. Now 2 also having 6 power. Now after that you can easily get the square root as a 168. Look, 2 to the power 6 means 2 to the power 3 as a square root. 3 to the power 2 means 3. 7 to the power 2 means 7 and its multiplication is 168. So final answer, multiply given number by 2, then the square root of the product is 168. Next question, find the numbers between consecutive perfect squares, 4 square and 5 square. Recall the pattern. Smaller number is 4. So 2 multiplied by 4 equal to 8. How much it is easy. Same way, find the, look, here also explanation is given. Pattern is given. Everything is given. Okay. Here again 9 square and 10 square. So smaller number is 9. Look, 2 multiplied by 9 and 18 numbers. And if you have to make the list, then you can write the list by this way. So do not forget the formula n square n plus 1 bracket square, and it is giving us the formula to n. Math problem solution guide. Pattern recognition in Pythagorean triplets and prime factorization through grid count. Let us see Pythagorean triplets pattern. Let us learn in this pattern. I have simplified this pattern as a clear exponent. Look, in the first pattern, 1 square plus 2 square plus 2 square equal to 3 square. So if you see these two numbers and if you multiply these two numbers simply 1 into 2, then you are getting 2. And in the result you have to add 1, then 3, means 2 plus 1 means 3. So it is a square of 3. Now you can check 1 square is a 1, 2 square is a 4, again 2 square is a 4 and 3 square is a 9. Check 9 equal to 9. So it is applicable everywhere in all the pattern. Look, 2 into 3 equal to 6 and here 6 plus 1 equal to 7. Same way, 3 into 4 equal to 12 and 12 plus 1 equal to 13. So this is known as a Pythagorean triples pattern. Okay. Next problem, counting tiny squares. You can see in your textbook the grid is given. Count the grid. 10 columns and 10 rows are there, means total 100 unit. So it is a square. The pattern alternates rotated diamonds and aligned grids across the full 10 by 10 layout. So 100 equal to what? If you make the prime factorization, 2 square multiplied by 5 square. So successively if you divide 100 by each factor, look, 100 by 2 then 50, 50 by 2 then 25, means this is completed. 25 divide by 5 then 5 and last 5 divide by 5 means 1. This also satisfies prime factorization. Key takeaway, 2 prime bases 2 and 5 each squared, a clean, elegant factorization that reflects the 10 by 10 structure perfectly. Next and last topic is cubic numbers. Exploring the power of 3. A visual journey into one of mathematics' most satisfying patterns for grades 8. What is a cubic number? Let's define. A cubic number is what you get when you multiply a number by itself 3 times. We write is as n cubed. It is read as n cubed. Key example, 2 to the power 3 is what? Repeated multiplication of 2 3 times and answer is 8. So 8 is a perfect cube. The exponent 3 tells us you how many times to multiply. The result is always called a perfect cube. The next question, how many unit cubes in the given question? A cube has a side length of 1 centimeter. How many unit cubes of side 1 centimeter fit inside? So, two questions given to you. I have written the instruction, think it through before flipping to the next slide. So 1 cube equal to 1 unit cube and 3 centimeter if given, then 27 unit cube. Why? Because 3 to the power 3 equal to 3 multiplied by 3 multiplied by 3 3 times. So side length cubed equal to total unit cubes inside. So this picture is also showing the things. Okay, side length, measure the cube's edge in unit. Cube the number means multiply the side by itself 3 times. Means this direction is showing what to do exactly. Means if you want to find side length, then what to do? If you want to find the cube the number, then multiply the side by itself 3 times. And the total unit cubes, what? The result is the count of 1 centimeter cube blocks. Look at the picture. The first 10 cubic numbers. 1 cube, 2 cube, 3 cube, 4 cube, 5 cube, 6 cube, 7 cube, 8 cube, 9 cube and 10 cube and n cube. What patterns do you see? Look at the last digit of the first 10 cube numbers. In 1, 1, 2, 8, 3, 7, 4 means what you have to understand that way. So in that way you will get the last digit for given respective 1 to 0. So last digit patterns. Cubes can end with all type of number. Look, 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Each digit 0 to 9 when cubed always produces one specific last digit. This lets you quickly rule out numbers as perfect cubes. So perfect cubes and odd numbers now. Here is a beautiful hidden pattern. Consecutive odd numbers always sum to perfect cubes. So look, 1. 1 cube equal to 1. Here we have taken 1. Now only first odd number. Now take two odd number. Just the number 1. Already a perfect cube. 1 is a perfect cube. Now take two odd number. Next two odd number 3 and 5. Then you will get 8. And 8 is a cube of 2. Two consecutive odd numbers sum to 8. Now in the third step, here you took up to 5. Then the next number is 7, 9 and 11. Means in first only one number. Here two number. Here three odd number. Then the sum is 27. And 27 is a cube of 3. Okay. Three consecutive odd numbers sum to 27. Same way, you can check for 4 cube equal to 64. It would be 13 plus 15 plus 17 plus 19. Can you verify it? Finding cube roots. Next topic. The cube root, the symbol is in that way. Is the reverse of cubing. You find which number was multiplied by itself 3 times. So find the cube root of 64. Which number cubed 64? Which number cubed gives 64? Find. Same way, find cube root of 512 and cube root of 729. Same concept, which number cubed given number. So look here, answer. 64 is cubed by 4. So 4 is the cube root. 512 is cubed by 8. So 8 is the cube root. 729 is cubed by 9. So 9 is the cube root. Memorizing the first 10 perfect cubes makes finding the cube roots quick and easy. No calculator needed. Next question. Is 500 a perfect cube? Let us check. Can 500 be written as n cube for some whole number n? Use the factor triplet method to find it out. So make the factor. So you can see here, okay, 2 only 2 times and 5 3 times. So for a perfect cube, every prime factor must appear exactly 3 times. Do the 2's form a complete triplet? So answer is what? No. 500 has 2's but only 2. 5's grouped with extras. It is not a perfect cube. Now, cube roots and cube numbers. Now, let us set the problem with cube roots and cube numbers. Question 1. Find the cube roots. Find the cube roots of 27,000 and 10,648. So, break 27,000 into known cubes. 27,000 means 27 multiplied by 1000. 27 is a cube of 3 and 1000 is a cube of 10. And as per the exponent law, keep the power 3 as a common exponent. So you can easily get 30 to the power 3. So cube root of 27,000 is a 30. Same way, find the cube root of 10,648. Here you have to make a prime factorization method and then you can get the cube root as 22. Verify this by multiplying. Your answer is correct or not. Now make a cube number. What number will you multiply by 1323 to make a perfect cube? So make a factor, then identify, then multiply, then verify. This process we have done in also the square number. To form a perfect cube, every prime factor must appear in groups of 3. Since 3 is already complete here, but 7 only appears twice. So we multiply by 7 to complete the triplet. So result is after multiplying 9,261 and then its cube root is 21. Now some true or false for odd cubes. The cube of any odd number is even. Let us check. 3 cube is 27, always odd. 5 cube is 125, always odd. 7 cube is 343, always odd. So odd multiplied by odd multiplied by odd, always odd. So this is false. An odd number multiplied by itself 3 times always stays odd. Next, true or false? Perfect cubes ending in 8. There is no perfect cube that ends with 8. Let us check. 2 cube ends with 8. 12 cube also ends in 8. 22 cube also ends in 8. So answer is what? False. Numbers ending in 2 always produce cubes ending in 8. The pattern repeats every 10 numbers. Now next, two-digit cube properties. The cube of a two-digit number may be a three-digit number. So let us check. 5 cube equal to 125. It is three-digit number. A perfectly valid because three-digit. So question is what? The smallest two-digit number is 10 and 10 cube equal to 1000 and it is 4 digits. But 5 is technically the edge case. This confirms the statement is true. So what we are learning here, from 5 to 9 we are getting 3-digit number. But for 10 we are getting the 4 digits. So for 5 to 9 it is true. The second question, The cube of a two-digit number may have 7 or more digits. Look, 99 cube. So 99 cube, it is giving 6 digit only. But 100 cube, it is giving 7 digits. So it is not true for 99. So though 100 is a 3-digit number, this shows the boundary 2-digit cubes can approach 7-digit territory near the upper limit. Cube number factors. Cube numbers have an odd number of factors. Let us see. 8, 27, 64. 4 factors. Look. 1, 2, 4, 8. For 8. 27, 139, 139, 27. And 64, 1, 2, 4, 8, 16, 32, 64. So 7 factors. So it is odd. So perfect square always have an odd number of factors that we have seen because one factors pair with itself. Cube numbers like 64 are also perfect squares and perfect cube. So we can get a 7 factors and number of factors are odd. Perfect cubes that are also perfect square like 64 always yield an odd number of factors. Guess the cube roots. Each number below is a perfect cube. Use digit patterns and estimation to identify the cube root. Strategy tip. Look at the units digit of the cube to predict the units digit of the cube root. For example, a cube ending 3 means the root ends in 7 and a cube ending 8 means root ends in 2. So look here. Cube root of 1331. So its last digit must be 1 here. So it is a cube of 11. Same way, here 3. So as we read here 7 and it is 17. Cube of 17 means so cube root is 17. Same way, if the last digit is 7 then we may get 3 as the last digit of the cube root. So cube root of 12,167 is 23. Same way, for number 32,768, 8 is there, so we can get 2 as the last digit of its cube root, and answer is 32. So which is greatest? Comparisons are given. Look, 67 cube minus 66 cube, 43 cube minus 42 cube, 67 square minus 66 square, and 43 square minus 42 square. Look, cube and square of the same number. So if you make it, if any pattern is applicable, then apply the pattern, then get your answer and verify which difference give the greatest. Okay, so do this activity. So with this check your knowledge. We have completed the lesson. The worksheet you may get in the description. So check the description, get your worksheet, complete the worksheet. If any doubt is there, then comment. Wait for the next video. In the next video, we will cover the new lesson. Till then, continue practicing, subscribe and like the channel Time to Cram for more such academic videos. Thank you.